So with the binomial probability distribution, or the binomial distribution, that random variable needs a fixed number of repetitions, okay, where the outcomes are successes or failures. But with the Poisson distribution is similar to the binomial distribution, in that the random variable represents a count of the total number of successes. The major difference, your book points out, is that between the two distributions, the Poisson does not have a fixed number of trials. So what does that mean? That n, like we worked a problem out where n was equal to 20, or n was equal to 30, or n was equal to 5. We don't have a fixed number of trials. Instead, it uses a fixed interval of time or space in which the number of successes are recorded. So what's the big difference? Instead of a fixed number of trials, it uses a fixed interval of time or space. All right, so your book points out that theoretically there's no upper limit on the number of successes, though large number of successes are not very likely. Okay. Also, with the Poisson distribution, the word success may not actually be what you would think in your mind of success. Everybody wants to be successful in life. Everybody wants to be successful in this class. This morning I just wanted to be successful in coming to work on time. So, success is good, but not always. What if I was looking at a life policy, a life insurance policy, and I'll probably have $200,000 or $250,000 in life insurance, but for me to successfully get that life insurance, I have to die. So it's not very successful for me, but it is considered a success if I get that life insurance policy, right? I won't get it, somebody else will. But success isn't always a good thing. Insurance companies may think of a wreck as a success. It's not really a success on their bottom line, but when they're calculating probabilities, they have to think of it as a success. They successfully crashed, I guess, not successfully got to work safe. Your book points out that a number of these could be airplane crashes, oil tanker spills, car accidents, things that happen in some period of time. Life insurance policies collected. When you talk to an insurance agent, they make those cancer policy. I have a cancer policy. They make all those sound good because you'll be prepared, but you don't want to collect on that cancer policy, do you? No, you don't. So, that's not the only thing. Think about things that arrive on time, like maybe from the time when you order something to when it's delivered to your house. Maybe Amazon has a 2 to 5 day delivery time or something like that, or some other business. Well, they want to figure out when it's successfully delivered in that interval. Of course, they're hoping that it's delivered quicker, right, rather than longer, to make you more satisfied. So these types of experiments that you could look at that are influenced by time, which is the way the world works, those can be described using a Poisson distribution. Okay, so that's what we're actually doing. Now look at this formula for the Poisson distribution. It is a little, it's very small, but it's a little intimidating because of the types of symbols and the variables that are used. All right, so the probability that the big X equals some other X, you know, this is exactly this, you know, that this equals this number, is e to the negative lambda times lambda to the x over x factorial, where x has to be a counting number. We can't have any negatives there. And I'll tell you what these variables mean. All right, now, we've all had college algebra, so we've all, at one point or another, so we've all seen exponential functions, like e to the x. That's an exponential function, right? Well, what is the e? It's not a variable. The e is a constant, kind of like pi. Everybody's used to pi because pi is usually kind of easy to understand. You know, we talk about circles and we talk about a radius and everything. Well, another number that happens a lot in nature and is used to describe decay, growth, things like that, is e. E is an actual number, just like pi is an actual number. You know, if I go to the calculator, on this calculator I have to hit inverse, but if I want to show you what e is equal to, if you have an e to the x button on your calculator, if you put in a 1 and then you hit that button, that's the value of e. 2.71828182845 whatever. So in physics, you know, if you have a physics class, there's a good chance you've seen e. You've seen the exponential e. If you haven't, you will. So that's what e is, about 2.71828 something. It just keeps on going on forever, no patterns established, and it happens a lot in nature. All right, lambda is equal to the average number of successes. And I'm going to put the successes in quotes because I told you successes aren't always successes in our mind, but in the probability realm, they can be different bad things. All right, the way that you pronounce that, L-A-M-B-D-A, lambda. One important feature of the Poisson distribution is that the variance is equal to the mean. All right. So usually what my students have problems with is, if they have problems with Poisson distribution, is they have trouble raising e to this negative power. I've had a student email me this semester and said, I can't put the e in the calculator right. So if I need to put in, say, e to the negative 5 power, then, you know, look at your calculator and look for the e to the x button. When you put a number in and then you push e to the x, it's putting the number that you put in the calculator where that x is. So if I wanted to say e to the negative 5, I would put in a negative 5, and then on the Windows calculator you have to push the inverse button and then e to the x. Okay? So e to any power is not going to be negative, and it's not going to be 0. It never will. Whether you raise it to a positive or a negative power, it can never be equal to 0. It can approach 0, but it can never be equal to 0, and you will never get a negative number out. Okay, so if I needed that for my formula, that's what I would be using, that big long decimal. Okay, so it would be good to have that in the calculator and then say times and then do your other work. Now, let's work through this example real quick, where quick is a relative term. There's an example here in the PowerPoint that says, suppose a bank has one automatic teller machine. Customers arrive at the machine at a rate of 20 per hour. So you already hear a rate, 20 per hour. What is the probability that no one will arrive in a 15-minute interval? So we want to know the probability that no one will arrive in a 15-minute period. Okay, so we're probably going to need to think about minutes in terms of hours, because we were given that the average rate was 20 per hour, right? Average rate that people visited the money machine. I don't go to a money machine. I have a money tree. I just go in the backyard and pick some. Average rate of 20 per hour. All right. So since we were given one part with an hour and one part with minutes, we're going to need to either calculate things as minutes or hours. So it's pretty easy to change 15 minutes into hours, right? Because 15 minutes is 1/4 of an hour. Really, it's 15 over 60, so 1/4. So this right here, this 15 minutes, that's 1/4 of an hour. All right, so the probability that x equals 0. So think about this formula that we had up here, the Poisson distribution formula. You have e to the negative lambda times lambda to the x over x factorial. Okay, so that's e Alright, now before we plug in anything, we need to know how to come up with the lambda. On average, in 1/4 of an hour, what would the average rate be? So let's think about this. Think about it. Seriously, think about it. On average, if 20 people come an hour, then on average, how many people would come in 1/4 of an hour? So just see that in your head. In 1 hour, 20 people come, on average. In 15 minutes, which is a fourth of an hour, on average, how many people would come? You just say 1/4 of 20, right? It just makes sense. If it doesn't make sense, you need to read it several times and think about it. So the lambda here on this particular problem, since we have a 15-minute period, that's what we're trying to figure out the probability in any given 15-minute period. If we know the average is 20 per hour in the 15-minute period, that's going to be 1/4 of the 20 per hour. So 1/4 of 20 is 5. So our lambda is equal to 5 in this problem. So that's e to the way the formula is, it's to the negative 5. Now, remember also, we're wanting to know the probability that no one will arrive. So the lowercase x is equal to 0 because we don't want any, we want to know the probability no one arrives. So I have e to the negative 5, and that's important because the second part of the formula is lambda to the x, and that's the little x. So that's going to be, what was lambda? 5 to the 0 power over x factorial, 0 factorial. Remember, 0 factorial is defined as what? 1. Yeah. Now, you remember whenever you were learning about raising things to powers, and you learned about raising constants or even variables to the 0 power, what happens? See, it's another one of those, where am I ever going to use this? Well, raising this to the 0 power, so that's going to be what? 1. Anything to the 0 power except possibly 0. I had to throw that in there. It's always equal to 1. So this is going to be e to the negative 5 times 1 divided by 1. So really it's just going to be e to the negative 5. So depending on how many decimal places that I want to round that to, so 5 negative, user error, 5 negative inverse e. So right there, if I wanted to round that to 4 decimal places, it would be 0.0067. 0.0067. That's 0.67%. So 2/3 of 1%. That's a really small, really small number of people. So the probability that nobody comes within 15 minutes is 0.0067. If on average 5 people come every 15 minutes, the probability no one will come is very small. And it would kind of make sense if you think about it. And that would apply to anything. If the whole thing about the money machines really doesn't register because you haven't used cards, well, think about if you were owning a business and you were producing 20 items an hour. Like maybe you work at, I'd always thought it would be kind of cool, maybe I'm wrong, to work at like a snow cone stand, maybe to make a little extra money. If I was making 20 snow cones an hour, which would be about 5 every 15 minutes, right? If I want to know the probability that nobody's going to come and get a snow cone in 15 minutes, I could figure that out. The possibilities are unlimited. The hard things to figure out in the real world is what is that average, and then I can use a formula like this to figure out a probability. Now, let's see what the table shows us in the back of the book.
Can I ask you one question?
Yes, you can ask me a question.
E is always going to be a negative.
Yeah, the way that the formula is, you have, this is negative lambda, so you're always going to be raising it to a negative power. But then when you write the lambda here beside it, don't make it negative. It has to be positive. Now we have positive 5 to the 0 power. So it's not always going to be to the 0 power. Like if I wanted to know the probability of, let's do this same problem, and I want to know the probability that I'm going to get 8 people within that 15-minute frame. Then this would be e to the negative 8 times 5. That would, well, I mean, e to the negative 8, sorry, not negative 8. We're using the same numbers. I apologize. The lambda is 5. So it would be e to the negative 5 times 5 to the what? 8th over 8 factorial. So this problem would give us the probability that within a 15-minute period we had exactly 8 people come through the line and get money. So to work this problem out, I actually have to work all this other stuff out. So I have e, the negative 5 didn't change because it's still the same average people coming every 15 minutes. That I just referred to the same problem. So if I say negative 5 e, then I might have to say this times 5 to the 8th. So times 5 raised to the 8th. So that's the numerator. Divided by 8 factorial. That's a really big number. 8, and then I'm going to hit this factorial button. Equals. So if I rounded that to 4 decimal places, that will be 0.0653. So that's a 6.53% chance that in any given 15-minute interval at this particular bank, exactly 8 people would come through. This PowerPoint then goes through a problem of at least 3. Okay? At least 3. And we're going to look at those tables. But what does at least 3 mean? X is greater than or equal to 3. Now we're going to have to use some math sense here because remember, what's the difference in a binomial distribution and a Poisson distribution? A binomial distribution has a set number of trials. A Poisson distribution theoretically would work for an infinite number of trials. While we can't have an infinite number of cars come through that bank, we could have a lot come through that bank. So the probability that x is greater than or equal to 3, we have no top number to go to. Like we can't say the probability x equals 3 plus the probability x equals 4 plus the we don't have a top number to stop at. So we do have to use the fact of 1 minus the opposite of this, the other stuff. Because we know the probabilities have to add up to be 1. We can say that the probability that x is greater than or equal to 3 is equal to 1 minus the probability that x is less than 3. Because that would be everything else, right? So that means 1 minus the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. So that will give us the probability that x is greater than or equal to 3. And then we would need to work out each one of these. Let's see if the tables could help us out on one like this. Okay. I was just glancing here at this problem here. Look, there's another little section showing you how to do stuff in the TI calculator. So, will it make your life easier? Maybe. Okay, so let's go to the tables. We have to get used to using tables. We're going to be using them more and more. Alright, Poisson probabilities. X equals lambda equals. So notice what's changing here. The lambda's changing. The X, you see, is just getting bigger and bigger and bigger in this column. The lambda is what's really changing in these other columns. Okay, so our lambda was what in our problem? Our lambda was 5. So can we even use this table? Let's see. So we have to go to a lambda of 5. Here's a lambda of 5. Look, when lambda equals 5, x equals 0, it says 0.0067. Is that what we got when we worked out our problem? We got something really close to, yeah, right here, 0.0067. So yeah. Alright, so what we need to do, if we want to use a table to help us work this, even though we could work it out all the way, our lambda was 5. We need x equals 0, which we already have, x equals 1, x equals 2. So here's 5, and then we need x equals 1, x equals 2. So 0.0337. Remember, we know the first number. It was 0.0067. So this one here is 0.00, or no, 0.0, let me go back, 337. And then we need x equals 2. That's 0.0842. Alright, so I have 1 minus all that. So I'm just going to do that in a calculator. I can just subtract each one of those. So 1 minus 0.0067 plus 0.0337 plus 0.0842. Oh, I think I put plus. It's minus, minus, minus. So I don't know why I was adding. You might want to add those together and then subtract. Maybe that's what I was thinking. Alright, so I got 0.8754. So what does that actually mean? The probability that 3 or more people will drive through that bank to the machine within a 15-minute interval is 0.8754, or 87.54% of the time. More than 3 will drive through in any 15-minute given interval. Alright, so once you understand what you're doing, You can use the formula or you can use the table. And of course, we couldn't use the formula if our lambda is not listed in the table. Alright. The last type of distribution is the hypergeometric distribution. Alright, and that's what we'll be covering next.